Yeah. Uh, a very good afternoon. Myself, I'm Chaitanya. I'm a core faculty member of National Water Academy. And today the session is on introduction to GIS, as well as we will have some hands-on on generation of contours and basin delineation. It all depends on you on how much receptive are you will be. Whether if you want to complete, I can stay till 5:30 or even 6, so that we can complete it. Before going for hands-on session, I will take some means I will be introducing basic concepts of GIS and then something about remote sensing. Uh, Only if you are in need of it. If you are already have some understanding or background knowledge of GIS and remote sensing, then I will go quickly. Otherwise, I will spend some half an hour or so in explaining the concepts. Have you means how many of you are well means have prior knowledge about GIS and remote sensing? Little bit. Anyway, I will also only be touching very basics only, very basics. Before going, why we are talking of this topic is you must have heard about IWRM. In for Indian context, we term it as IWRDM because we still have to develop our water resources. Apart from management aspect is also becoming very important. When we say IWRDM or IWRM, there are certain prerequisites. Something should be in place, like legal framework. There has to be a river basin organization, institutional arrangements, financing instruments, some mechanism to resolve the conflicts. But most key part is the data and information systems. Unless you have the data, you cannot make informed decisions. So, and then you have to have a very clear understanding of the hydrological processes. The hydrological cycle, water cycle, as you know, it has many components: evapotranspiration, precipitation, etc. The traditional point measurements, whether it is of rain gauge or discharge sites, they measure at points. We cannot have synoptic view, or you cannot visualize in space and time how these parameters are changing. And there are certain components of hydrological cycle like evapotranspiration, which are very difficult to measure. And evapotranspiration is a measure of actual water utilization. How much water is being utilized in any irrigation command? We are talking mostly about irrigation, so we don't have any very estimate. We don't have any way to measure the how much water is being utilized. We only have data of canal releases, but how much is actually being utilized in the fields, we don't. In the field, we don't know. For IWRDM, the data and information systems are key. If we want to have better management, we need to measure, or we need to have some estimate of these various components of the hydrological cycle. And for that, we can take use of geospatial technology. And this geospatial technology is a broad term which includes GIS, remote sensing, GPS, and other things. We are talking of GIS and remote sensing today because the quantification of, as I said, the traditional methods of measurement, point-based measurements, are not sufficient for assessing the spatio-temporal variation. Whereas remote sensing imagery, satellite imagery, as well as many other derived products, we will be working on one derived product, which is a digital elevation model. Digital elevation model is a data set which gives information about elevation of that particular location on the surface of the earth. It is a derived data set. It is not an exact data. Means there will be some errors, so we have to process it. We will use it for catchment delineation. Retrieval of information from remote sensing imagery, it provides an alternative to quantification of hydrological parameters. You take precipitation, you take evapotranspiration, you take soil moisture. There are data sets which provide you some estimates in quantitative terms. It depend. Only thing that varies is spatial resolution, because the satellites are observing from the top of the atmosphere. Sometimes you have good resolution, sometimes you don't. it is not always possible to sense everything. The satellite remote sensing also has many limitations. Within this short period of time, I may not be able to convey that point, but I will try to. So let us come to first GIS. GIS stands for, as you all know, it is Geographical Information Systems. You must have heard about MIS, Management Information System. It is basically an information system. GIS is not a software. Software is one component of GIS. GIS software, when we talk of ArcGIS or QGIS, it is just a component. The important part, component of geographical information system is data, spatial data. Spatial data, generally when we see any data in Excel format, if it has also spatial component, latitude and longitude, then we can convert it into a GIS layer, and we can do many things with the GIS. GIS, it started with mapping application, but it has many applications for doing analysis, for visualization, for preparation of maps, querying. We will see some of them. So if you see the evolution of GIS, basically all human activities, they are associated with some locational aspect, and if you know that locational aspect, it will be easy to analyze things. And we always, why do we require, like, what is the purpose of maps? Why do we use maps for? Maps are representation of reality. Because reality is very complex, we try to represent it in simpler way, where we can visualize many, whether it depends on whether the theme of the map. We can have thematic maps. There are different types of maps, but those old paper maps, once they are prepared, you cannot modify them. You cannot make any changes. And if you want to try to incorporate too many elements or too much information in a map, the map will become very clumsy. It will be, you will not be, it will not serve the purpose. Ultimately it will not serve your purpose, which is simplification of the complex reality. So representations, basically it help us to assemble for knowledge than is possible on our own. When we talk of GIS, it has its origin from this example, where this is an street map of London, some part of London, where these are the streets, and these dots are people who died due to some cholera outbreak in 18th century, like 18th century, 1800s, 19th century. They had information about the house number, basically. So even if you have suppose you imagine an Excel file, all of you must have worked with Excel file. It has it has the same kind of information. You have serial number, name of the patient, house number, age, sex, etc. Suppose you also have this house number, someone has depicted it in the form of a map. And what you cannot see in Excel and what you can see here is, you can observe clustering here, grouping of deaths. So, the cholera the deaths due to cholera outbreak in that particular part, in that city, happened in a particular part of the city. That is one thing. And another thing is, they also mapped water pumps, tube wells from those time, which were contaminated, which are serving this area. That time it was not very well known that what was the cause of cholera, but still they deduced that the areas being served by contaminated pumps, they are having these deaths. So one thing you saw, one thing is clustering. You identified the hotspot, and the second thing is you related it with the cause. The same information, when it is in the form of Excel, you cannot deduce it if it is in a tabular form. But if it is represented in spatial manner, if provided it has spatial data, if without house number, in our case mostly we will be dealing with global coordinate system, latitude and longitude. We will see one text file having latitude and longitude, and we will try to convert it into GIS layer. So this kind of this is the classic example. We will find it in many GIS textbooks, how GIS has evolved. Like this is one example. So digital representations, again, from the conventional paper maps, digital representations are much better than the conventional paper maps, because you can find, you can choose what element to you want to show, depict, and you can do, if you have a GIS layer, it will be possible to do the query, take subset of anything, and analyze. Like I will come to few examples. But before that, what is GIS? GIS, as I said, it is not any software. It consists of software as well as database. Software database is very important, and ultimately the aim is to depict the real world. If you want to abstract or simplify, and you want to produce some results in the form of maps, reports, and charts. And the purpose is to view the data, to understand data, question data. Questioning is not possible with paper maps. Interpretation and visualization. Visualization is possible, but interpretation, seeing the relationships, patterns, and trends, that is not possible with conventional maps. The questions that GIS can answer, like where are particular features found. If you have a GIS layer, you can identify the water bodies, you can identify the vegetated areas, that you can also do in paper map. But you can select subset, like if you want to select only the cities which are greater than population, say 1 million. So that you can run a simple query in GIS software and only depict only those cities. That kind of possibility will be there. And then geographical patterns, as I had said, seeing the pattern or relationship between two events, deaths due to cholera, and then another is the water supply points. Then trends, how a city has grown and in which direction it has grown. That will be very helpful for urban planning. If you have maps from, say, satellite imagery from, say, 1900, 1990s, 2000, say, after every 10 years, you have a map of a Guwahati, for example. Now, if you see the trend, how it is growing, the city is growing and in which direction it is growing. If you prepare GIS layers, you can use it for prediction of the growth in any along any highway or along any particular locality along the river. That trend you can predict. The land use, land cover change trends, also all such things can be predicted. And where do certain conditions apply, knowingly or unknowingly, you are already using, means you must have, you are using GIS through navigation tools, Google, road, Google navigation, and many other things. Many apps make use of GIS. But if suppose if you have a problem in front of you, like if you are a supermarket chain owner, you want to set up a store, your objective would be to have the maximum number of footfall. And suppose you have only want to apply, you have data of density of population, some layer, GIS layer, and another data, a road network data is there, that is digital layer. And you run a query, you want to have locations which are less than, say, 1 kilometer from the road network, and you want to have you want to identify the locations of locations having density of population, say, greater than, say, 200 per square kilometer. And a combination of these, you can run a query, a simple and or operations in Boolean algebra. If you have done that, you can run that in SQL language. It is very simple, and you need not learn any new language. The everything you will be seeing raster calculator. There are ready-made buttons where you have to click and run a query. You select an expression, one expression or two expressions or multiple expressions, and then you see where the conditions apply. And then the supermarket, if you are the supermarket owner, chain owner, you can identify the places where you can set up your store. And implications, say for example, if you are building a dam across a river, and if you have a digital elevation, model. Digital elevation model is a, I will come to the raster and vector, but digital elevation model is a raster GIS layer where each pixel has information about elevation. If you have a very good digital elevation model, and if you know the FRL of that particular project which is about to come, you can see what will be the submergence area, and that will be can be used for planning rehabilitation measures R&R. So these are very few things that I have touched upon, and our purpose is not to learn GIS as a theory, but application point, and that too from hydrological application. GIS has its applications in variety of fields, health, traffic, many multiple fields. Whereas from hydrological point, we will see most of our applications. One thing is delineation of river basins, which is a basic unit for any planning, water resources planning, as well as management. And then using remote sensing imagery, satellite imagery, estimation of hydrological parameters, the one which I had talked about in the initial slides. You can estimate precipitation, you can estimate ET, all those things, and then you can have a water balance. You can do water balance at any scale, provided you have very good resolution, imageries and products, the ET products, all those things. So data, as I said, is very crucial for GIS, and in GIS, data has two components: spatial and non-spatial. Non-spatial data is known as attribute data. Just like in Excel, all those columns, serial number, name, all those things which have nothing to do with the location, they are non-spatial data or attribute data. Whereas there will be two, if you have locational information in the form of here, there in that example, house number, but if you have longitude and latitude, there will be two columns, that is the spatial data. So GIS data consists of location as well as attributes. For example, this is a GIS layer, which you will see in the GIS interface. You will see something like this. Imagine it is a map of assembly constituencies of in this particular district. So you will see the polygons. You can label the name and you can show. But if you can store the information related to this particular constituency, its population, density, area, many things. You can, these are the attributes for each this particular location. You have these attributes. They can be stored in a attribute table like in the normal Excel sheet. So here what we have the added advantage is you are showing it in the means you are depicting spatially. You have the spatial information also. So any data, texture, any system, any structural data if you have, and if you can add locational element to it, then you can convert that data set into a GIS layer. There are two basic, there are two data models in GIS. Anything can be represented in GIS either in vector data or raster data. Have you heard of these things? Vector data model, raster data model? Can anyone tell me what is vector data model, what it is used to represent? What all features we represent using vector data model, and what all features we represent using raster data model. I already talked about DEM, digital elevation model, which I said it raster data, it is a raster data. Anyone quickly please?
Raster data represents XYZ and on the survey. Vector data.
Sorry sir?
Vector data represents XYZ.
Vector data.
Vector data.
And raster?
Raster data
No. Even vector data or raster data will have spatial and non-spatial component, because both are GIS data models, and GIS means it will have spatial compulsorily. Without spatial component, we will not term it as GIS. Basic.
That's opposite we consider the raster data. Opposite we consider opposite as a raster data.
No, I will tell. So actually, vector data is used to represent discontinuous data or discrete data. discrete data in the sense, say you are looking from at map of India, and cities are discrete cities, capitals of all the states, they are discrete points, right? Rivers, they are discrete lines. Lines are not in, no, I don't mean straight lines, but they are line, they are lines are basically collection of points. If in vector data, everything starts from a point which will have coordinates x and y, generally universally accepted coordinates. Spatially, we keep it as longitude and latitude. X coordinate as longitude, y coordinate as latitude. Why? Because on x-axis, longitude varies, right? So it starts with a point. You can have multi points like multiple cities, and if you want to represent something like a highway or a canal or a river, then you can identify some known points along the river or canal or highway, and you can collect the coordinates of that particular point using GPS, and then you can join them, then it will become a line. And multiple lines, if it is a river system, there will be multiple lines. If it is a road system, railway line system, it will be multiple lines. So points, multi points, lines, multi lines, and then we have seen one polygon constituency, or what I said, that is nothing but a area we want. So for representing area, that will be used for like if you want to represent a state or district or city at India scale is a point. But if you are showing Guwahati city map, then it will be a big polygon. It also depends on scale. It also depends on scale whether you want to represent anything in vector or raster, or whether to represent it as a point or a polygon. So yeah, polygon is nothing but a line which is closed, or the origin point and the end point are coinciding. So when you want to draw any closed area, you start from one point and you come back to the same point. Then it will enclose some area that will be used for representing any region. It can be used even for representing land use, land cover area, agricultural land, vegetated land, populated land, anything. So these are all are discrete points, lines, polygons. These are discrete. They are the vector data model. Whereas raster data model is generally used for representing continuous data. Elevation is a continuous data. Elevation varies from here to here to here. Every point has an elevation. So to represent elevation of a particular region, you can divide that region into grid, and every grid, every pixel will have the average elevation or whatever you want to. You can even show maximum elevation. Generally, we go for average elevation. So that is a raster data model, where the size of the pixel, depending upon whether you have a very good sensor, you can have very fine resolution. Fine means the size of the pixel is very small, or high resolution. High resolution, small pixel. Low resolution, big pixel. So it is like the digital photograph that you take on mobile. You talk in terms of megapixels. How many megapixels? Or the scanner that we say DPI. The same with raster. So yeah, raster is used for representing continuous data. One example, elevation, and almost all hydrological variables, rainfall, evapotranspiration, soil moisture, everything varies continuously from point to point. Even though we measure it discretely at identified locations, but the phenomena as such is continuous. So we represent all the hydrological parameters as a raster data. So that is the basic difference. But again, it is comes with the qualification that it depends on scale. City at India, the scale is a point, whereas city at a large means larger scale, or when you are identifying smaller area, it is a polygon. So you can like this is an example. This is the real world where you have a forest area, where you have a lake, you have streams, you have river, and you also have some land like this is a lake, this is water, this is forest, this is marshland, grassland. Some land use land cover classification you have done. You can represent it in both ways, vector as well as raster. Generally, we go for discrete features for vector, continuous features for raster. But you can do either way. Like here, you represent all these areas as polygons, those areas. Lines, these are reversed by lines. So, this is the vector data model of this real world. The same thing, you draw a grid, and every grid, whether it is occupied by water, you can give some number, or you give the this attribute some, you can show the value, some value, one equal to water, two equal to grassland, three equal to something. You can store the same information in a raster. Now the same thing, you see another example. This is the real world of a urban area, a river. This is residential area, forested area. Here you have also elevation information, land use, land cover information. So the continuous variables, land use, land cover, are land usage. Like these gray pixels are urban areas, green pixels are forested areas, brown pixels are residential, blue pixels are river. You can define elevation also. You can define higher elevations in generally, as you see in Atlas physical map, higher elevations in brown and lower elevations in green, etc. Same. So these are the rasters. From this you can derive these two rasters, and also you can come up with location of these individuals, are location of houses, points, point vector layer, street map, a line vector layer. Then these bound the area enclosed by each like some locality information. These are the bound. These are polygons. So the same you can derive. You can make it into different GIS layers, and then you can lay over one over on the top of another. You can choose to represent what to, you can choose or not choose what to represent or not, for simplification purpose. That is, this is for conceptual understanding. We will not spend time much more on this. So this is the same thing that what I have said. Data can be modeled either as raster or vector. Vector data is stored as a pair of xy coordinates, starting with point, then line, polygon. Raster is stored as grid. Vector data is generally associated with discrete objects. Continuous data is better represented in raster format. Then there is something called georeferencing. See, you on any paper you can mark points, but you can even maintain accuracy, like you can draw Assam map, you can draw even districts, and you can even point cities, means you can mark the cities. But unless you have associated geographical information relative, and how the relative distance between features, relative distance, if you unless you you associate every point with some locational information, it will not be qualified to be called geographical data, even though it is depicting something. So generally, we have to go for suppose, say for example, you have an old map of Guwahati, paper map, which was made accurately at some point of time using physical surveys, using some and cartographers were involved. Now you want to make use of it. We want to digitize it. You can employ a very good scanner to scan. Then the output will be a raster file, because we are scanning. It will generate a pixel wise information, but it is not geo-referenced, in the sense it has no locational information. But you can say, where do I write? अच्छा इसी पे ये आप एक मैप ले लीजिए कुछ साइड बुलाना पड़ेगा suppose you have this map, you have scanned it. Map itself may be having grid of latitude, longitude and latitude, right? So this point location, this grid, this point location, that longitude and latitude is known. So such known points, you identify known points which are known as GCPs or ground control points, whose location information is known. It is very easy to identify such. If the grid is not present, what you can do? You can go for a prominent landmark in the city. उसका use a GPS on your phone, or you can get coordinates of any prominent landmark easily on the internet. So you mark that. So you select ground control points. Minimum number is five in a map, or you can go for the many number of ground control points. And then what you do is you transform. Like you for known points you give the locational information, and then you apply a polynomial transformation, and then it will allocate for every point some longitude, some latitude, just like a transform mathematical transformation. So then this process is known as georeferencing. Why I am telling this is because this is the basic means if you want to generate a GIS layer from a hard map or a paper map, this is the procedure that you have to follow. Then once you georeference, a georeferenced raster layer can be used for generating vector layers. Once you georeference, there are tools known as digitization tools in GIS software. It is like just like you click on a button, and once you georeference, you have on this map there may be a river which is flowing in this direction. Then you can start with the digitization tool, and you can just click on these points and then draw a line and then save it as a vector layer, which is a line vector layer. And in the attributes, you can give its name, length, etc. Then you have created what you have created. You have created a GIS layer. So GIS layers, vector layers can be created from geo-referenced raster layers. Suppose if you are taking aerial photographs or satellite imagery, the sensors, they already do the georeferencing. They capture the locational information. So you can take a aerial photograph, satellite imagery, and you can do the directly digitization and then create the vector layers. So I hope you understood what is georeferencing. At least four ground control points, 4 to 5 ground control points are necessary, and they should not be at one place. They should be spread over the whole map. Even if you have only 4 points, four should be like in four different directions. Then it will be the transformation will be better. Otherwise, the error will be more. Error of association for other association of longitude and latitude will be more otherwise. So I think this is a repetition. I am skipping. You will get the slides. The input data for GIS, as I said, digitized as scanned maps, tables of data provided. What it should have? It should have locational information also. Then only it can be converted into a GIS layer. It should have one column of longitude and one column of latitude. It can be information about anything. It can be information about gauge sites or rain gauge stations. Then field sampling, then remote sensing and aerial photographs. These are the sources, already published sources like scanned maps. So you have this satellite imagery. This is how a GIS interface looks like. This is how a GIS layer looks like. A GIS interface looks like. There are many tools which are there. This is layers panel, where one layer is displayed. This is the layer which is a satellite imagery, and you can identify there is one river, there are houses, there are road network. You use your digitization tool. If you use your digitization tool and then start digitizing, you can create these layers, road network. I don't know whether it is visible or not, but simultaneously what you can do, you can, for every road you can save the non-spatial data, attribute data, by giving the name of the road, length of the road, type of the surface, anything that is associated with that road. Similarly, river, similarly, buildings. And once you create all those layers and remove that base layer, the satellite layer, you have created these many GIS layers. All these are, except for land use, all these are vector layers. Line or polygon are points. So you have this representation of the reality, right? So GIS can be used for querying, for measurement, like distance, minimum path analysis, buffering. Say, if suppose ASI site is there, and you have a rule that there should not be any no construction within 100 meters. I am taking very simple examples. Then, if you create a buffer around any feature, if it is a point, it will create a circular buffer. If it is a polygon, it will create a larger polygon, right? And you can see in that buffer area which are the constructions, the unauthorized constructions that have taken place. You can take remedial actions. Say then overlay analysis. One example. This is example for overlay analysis. This is an incidence of flood. There is a very high resolution imagery in the background, satellite imagery, where you can even see houses, everything. And then there is you have captured this information somehow, inundation area, along with information of depth from a flood event. Now, how to capture flood? That is another thing. Through remote sensing, it is possible. Along with remote sensing, it will capture the spread of water. Water is very easy to identify, but depth information you have to get from, if you have a digital elevation model, the elevation information, and if you know the water level, automatically you will get to know the depth. So you can overlay this one on the top of your layer, and you can see which are buildings were submerged, partially submerged, which agricultural areas were submerged. So that such things are be already being used for dispersal of insurance or damages, flood damages, crop insurance. Such things are being done in other countries. Already they are being done. So this is one example of overlay analysis. So similarly, these are the various kinds of analysis that are possible using GIS. Then one more thing is that is about GIS. I hope it is clear. GIS means spatial and non-spatial data. There are two vector models, vector and raster data models. What to represent when, and there is something called georeferencing. Georeferencing. Once you do georeferencing, georeferenced raster can be used for creation of vector layers, right? And then coordinates, geographic coordinates, we know earth is not a perfect sphere, it is a geoid. It is approximated as an ellipsoid. Okay, so every point will have longitude and latitude based on some assumed ellipsoid. Generally we go by this ellipsoid, universally accepted ellipsoid. You will come across this WGS 84, World Geodetic System 84. Like actual shape of earth is something like this, very irregular. We have approximated it to be a regular mathematical ellipsoid to have so that you can derive latitude and longitude information, or for doing any geographic analysis. Now that is fine, and this there are so many ellipsoids. Suppose you are doing a local analysis, there may be you can approximate this to be a ellipsoid here, something like this, which is exactly coinciding or very nearer to the geoid, but somewhere it is not exact. So this local ellipsoid can be used for analysis here, but it will not be useful elsewhere. But this WGS 84 is universally accepted ellipsoid, and this is known as generally when you hear about data, this GPS system uses this as data WGS 84. Otherwise, when in India, when the great trigonometric survey took place, they had their own datums. Kalyanpur datum is there. There are many. Even North America has their own datum. When they are doing local analysis, they still make use of local data. But for all general purposes, we use this universal data. So latitude and longitude are based upon this WGS 84 data. Now that is okay, but another problem is we have to deal with flat screens, flat maps, and Earth. Even if it is an ellipsoid, you have to represent this ellipsoid onto a flat surface. Then there will be some distortion. Distortions generally we want to minimize, distortions in Atlas. If you see, you may have even heard about it, like what you see the actual shape of Russia, Greenland, Canada, they appear very huge, they appear very big. That is because Atlas has one particular projection system which is known as Mercator projection system, which distorts the shape of those locations which are away from equator. That's why they appear very big. In reality, they are not that big. So when you are, that particular projection system is very convenient when you are doing any analysis near the equator, but not away from equator. So every region has there are n number of projections which are defined. For India, it is not a tropical country, or it is like subtropical. Some part is near the tropics, some part near the it means it is like in between. So we have a better projection system. The better projection system for India is conical projection system, which is known as LCC, Lambert conical projection. Like cylindrical, when I am talking of cylindrical, suppose you keep the earth here, it will be touching along equator. If you project all these points, the points which are on equator are exactly touching the cylinder. And if you open the cylinder, so these points are exactly represented, whereas other points are distorted. So for in tropical regions, cylindrical projections are useful. And cylindrical, there are many types of cylindrical projections. Some projections preserve area, some projections preserve direction, some projections preserve shape, depending on the application. When you are talking, when your application is navigation purpose, there the directions are important. When your application is something related to calculation of areas, where you have to preserve the area. So every time you try to see minimizing the distortion and the purpose for which you are using. So there are many projection systems. For polar regions, there is azimuthal projection, where you keep one plane on the top of both. There will be concentric circles. In Atlas, you will find one based on Arctic and Antarctic, where you will find these concentric circles. That is azimuthal projection. So why this projection is important, as we are saying, because we want to represent, or we want to do analysis, then you should not distort. There are many projection systems, and on each projection system GIS, they have a code. That code is given by what is known as European Petroleum Survey Group. So if you have global coordinate system GCS, okay, this is unprojected. That means you are only using the latitude and longitude without projecting it on any planar surface. That is known as global coordinate system. For that, they have given a code of 4326. You need not remember everything, but this one you will come across. And if you want to know code of any specific projection system, you can go to website spatialreference.org. Spatialreference.org, and then you can type the projection system, then it will give you the code. So this is the GCS, and there are many projected coordinate system PCS, like cylindrical types of many types of cylindrical, then conical many types of conical, then azimuthal many types of azimuthal, etc. And everyone has every projection will come with a code. And why we are talking of this projection? Suppose you have two different GIS layers in two different projection systems, then they have to be reprojected to the same coordinate projection system. Then only you can do any analysis. Otherwise, they will not overlap exactly. So whenever you get a GIS layer, you should look for its projection. What is the projection system? Whether it is global coordinate system, or if it is projected, then what is the projection system? So you have to put all the layers in the same projection system. Yeah. But when we are making use of this global coordinate system, we are dealing with degrees. We are dealing with latitude and longitude represented in degree minutes, seconds, which will not be convenient for any say measurement of distances or measurement of areas. It will not be convenient. So they have come up with this universal transverse Mercator system, which is a combination of many projection systems. It will give everything in SI units. Here the coordinates are known as eastings and northings. Okay. How it is derived is you instead of placing your cylinder in the you place the cylinder in the transverse direction, then your sphere will, like your earth will touch along one longitude, right? Then you take 6 degrees strip along that longitude, and then you open it, then it will be something like this. Half of it in northern hemisphere, half of it in southern hemisphere. Now here the distortion is minimal along this longitude, and somewhat distorted, but still it is within some range. Okay. And then you turn your cylinder, your earth 6 degrees again, and you again plot, you again project it. Then you by 360 by 6, you will get 60 zones. You have these 60 zones in the north and 60 zones in the south. So if you see India, it is lying within these zones of like northeast. I think it is 46 north, Assam part, 45, 44, 43. India starts from around 42 north to around 46 north. That is, if you are working in any particular state, you look where your location UTM zone is, and then you choose that as your projected coordinate system, and then you will get your results in SI units. Distances, areas, you will get directly in meter square, in meters. Okay, so this is a very convenient. This is not a single projection. Every strip, you can see it is a combined projection system. It will be useful for calculation of distances and for accurately calculating short distances between points. We will see these things when we do the hands-on. Now the time, how much time? 3:25. Some basic remote sensing, then I will go there. I will find out whether they have copied the copy हो गया data and copy. एक सिस्टम में नहीं हाँ, किसी को कुछ डाउट है? ठीक है, इज इट ओके? और I think I should fasten up because I am very going very detailed basics, which then we will not have much time for hands on. पर आपको जानना जरूरी है conceptual clarity कुछ चीज. I will quickly go through remote sensing. Remote sensing, the word as it says, it is sensing something remotely without in direct contact. The opposite of remote sensing is proximity sensing. We are talking of remote sensing because it is a key input for GIS. Apart from paper maps, all those things, that is a laborious process, scanning and but now you can sense with high resolution sensors in not just in visible region, but even other parts of the electromagnetic spectrum. Like our eyes, we are seeing in visible part of the electromagnetic spectrum, but we can have sensors which can sense in infrared region, near infrared, even microwave region. uh, so yeah, we will see that. So this part I am not going through what is remote sensing and what is electromagnetic spectrum. I think you all must be knowing that there is a very small part of this visible spectrum, starting from red region, green, blue, and here we will have after violet we will have ultraviolet, and then after red we will have near infrared, near thermal infrared, and so on. The wavelength is increasing in this direction, wavelength is decreasing in this direction, frequency the other way. So the naturally the sun's light, what you see is is a combination of this in the visible portion. The sun's energy is in this part of the wavelength only. And our eyes are tuned, we have evolved to sense this energy. I am seeing you, you are seeing me, and we are observing colors because our eyes they have been tuned to this. But there are also other parts of the electromagnetic spectrum in the sun's radiation, like infrared, which we can make use of. We have infrared cameras also, but we can make use of from we can design sensors to sense in that region. There is no naturally available microwave energy in the sun's radiation. In that case, you have to create artificial source of microwave energy. Like microwave energy is somewhere here. Why it will be useful, I will come. There are two types of remote sensing, passive and active. Passive is something which senses naturally available radiation, sun's radiation, like our eyes, like mobile cameras. There are two types of one thing, mostly reflected radiation. Vegetation is appearing green because it is reflecting more in green region. Water appears blue because it is reflecting more in blue region. Similarly, other colors, they are combination of primary colors. But there is also something called emitted radiation depending on the temperature of the body. Each of us are emitting radiation, but it is very feeble, that can be sensed by anyone from the top of atmosphere. But if it is a volcano or if it is a geothermal energy source, that can be seen. So that is passive. And then what is active remote sensing? As I said, microwave. There is no naturally available microwave energy in sun's radiation. So you put the source of radiation on the sensor, which will pass the radar sense pulses, and whatever is reflected again it captures. So why it is needed? Because sun's energy is not available during night time, and also when you have, suppose you are traveling in an aeroplane in during the monsoon season, this area particularly northeast, almost I think 6 months you won't see clear pictures from the satellite. If you are observing from on the top of above cloud cover, you won't be able to see anything on the ground. right? And if something, and this is the season where most of the flooding occurs. Suppose your purpose is mapping of floods, वो जल्दी copy कर दीजिए, हाँ? Then optical or visible portion will not be helpful. So you have to have something which can see through clouds. This microwave radiation with high wavelength, it penetrates to the cloud. It will provide you even night vision all through the year. So this there is a sensor known as synthetic aperture radar, which can be used for sensing even during night time and during monsoon season. So these are, I think I can skip. Basically, this is the sun's radiation, which is maximum in the visible portion. And here you don't have any sun's radiation. This is microwave radiation where you have no natural energy. These white portions are those portions which are known as atmospheric windows. Atmospheric windows means you can design your sensors only here. You can design in optical region, you can design in this region, but here either ozone or water vapor or carbon dioxide, they will absorb the radiation. So it will not be useful for sensing something from the top of atmosphere. So whatever radiation it comes, it gets scattered. Sky is appearing blue because of this one kind of scattering. It will be absorbed, and what it comes onto the surface, it will be reflected, absorbed, reflected. So this reflection is very key. Uh, just like we have our own unique signatures, every feature on the Earth's surface has something called spectral reflectance curve. Suns like this along the electromagnetic spectrum, in each region, how much any feature is reflecting, that is unique, and that will be useful for identifying that feature by seeing the multispectral satellite imagery, whether it is a vegetated area, whether it is a water body, or whether it is a cropland. That is possible. Like this is a simple example of vegetation. Equal amounts of blue, green, red, and yellow and infrared they are coming. Whereas vegetation reflects more in green, that we know, invisible portion, but it reflects much more infrared radiation. But our eyes cannot see it. And suppose you want to make use of this property of vegetation for marking, for mapping vegetation, then you need to have cameras which are sensors which observe reflected infrared radiation. So we design our sensors. So if you have this plot, this is a plot of percentage reflectance of vegetation. You can see it shows up after visible portion. This is the visible portion. Blue, green, there is a local maxima, but this is much more near infrared. Similarly, water, you see, it has, this is percentage reflectance, you can see 10-20% only. After infrared, it comes to zero. Like water will not reflect, it will absorb all radiation in infrared. So water bodies appear very dark if you see infrared imagery. Whereas vegetation will appear very bright or white in color. Basically, all satellite imagery will be black and white only. You combine them, you assign the red, green, blue to visualize or to give some them some color. If you are giving red color to red region, green color to green region, blue color to blue region, then it will be true color composite or natural color composite, which is the way which our eyes are seeing. Suppose you want to make use of the property of vegetation where infrared you also want to represent. So you can give red color to infrared reflection. Then wherever there is vegetation, it will appear bright red. So you give an NIR red color. Just like, I hope it is not confusing, but red color to this, green color to red. This is region, this is wavelength band, whereas this is actual color. Then it will create a false color composite. This false color composite will be useful for identification of vegetation, bright red portions. You may have seen many satellite imagery. Similarly, there are many false color. There will be only one true color composite, but there will be n number of false color composites. And each composite can be used for identification of particular feature, vegetation, agricultural field, urban area, etc. So these are the spectral reflectance curves of different. This is for clear water. This is for clear water. If it has turbid water during flood, because particles they may be reflecting more, it has higher curve. So you will find combination of, normally it appears blue, but because of combination of red and blue, they will appear brown in color. This is one curve. Similarly, this is for vegetation, which we have just seen. Broad leaf, needle leaf. Now I will ask you, just to make you feel involved, from this is a curve for, this red color is a curve for snow or ice. This is visible portion, infrared, near infrared, thermal infrared. And this is a curve for clouds. Suppose you don't know where you are looking at. How do you identify what is cloud and what is ice or snow? Without any locational information. Even though it may be the picture is Himalayas, but you don't know. You are seeing white. How do you know whether it is cloud or whether it is snow? You look at these two curves. They are almost similar here. Up till this point, they have the similar shape. That means in optical region, visible region, for our eyes, they will appear same. But if your sensor is also observing here, you see it has some point, at this point 1.4 micrometers, it has reflection of only 2%, but it has reflection of about 60. So clouds will still appear white if your sensor is sensing in this region, and snow will appear dark. So this is your eyes cannot do it, but your sensor can do. So if a sensor has capability to look in multiple bands, then we say its spectral resolution is very high. It will be useful for identification of many such features. So if you suppose there is something called now generally when we are talking of multispectral imagery, we will observe it in 9 to 10 bands, or say some 10 to 20 bands only. That is multispectral. There is something called hyperspectral imagery, where band is nothing but range of wavelength. This is one band. This is one band. So for each band, you will have a imagery in black and white. If you combine them by giving colors, it will be colorful. So in hyperspectral, the range will be very small. Then hyperspectral imagery, why it will be useful even for distinguishing within crops. Like generally, all crops have a similar shape of the curve. But if you want to distinguish from one crop to another crop, you are say broad leafed vegetation from coniferous trees from deciduous trees. The shape is same, but there is subtle variation that you can identify if you are if you are observing in multiple small bands. That is known as hyperspectral imagery. Anyway, that is so. Yeah, you look at this picture. You tell me what is the difference in these two. One is normal photograph, infrared photograph, that is written over there. But still, what do you observe? Normal photograph means this is true color composite. opposite. The way our eyes look when you are on a say small plane, it is taken from a small plane. The same thing you are viewing, your sensor also captured. This is a false color composite infrared photograph where NIR you are given a color red. That is why all trees they are appearing red, dark red. If it is grass, it is less. What you say? Lighter in color, but still it is. Now, but this portion you see, this is artificial turf that is not appearing in red. So you can easily make out that this is artificial turf because it is had it been natural grass, it will have reflection in NIR. It would have appeared red. So yeah, so that is how we map features and why it is important for mapping LULC and why it is again important for hydrologist point of view. LULC is what defines how much rainfall will convert into yield. If it is a forested catchment, there will be a different hydrograph. If it is a agricultural catchment, it will be a different hydrograph. How much water will come into the river. If it is an urban catchment, it will have high peak, smaller duration of hydrograph. Right? This is basic hydrology. So yeah, our purpose of remote sensing is to map features, even to map water bodies, to study over a period of time how the water bodies are changing in size and to how land use land cover is changing. It will become a input for hydrological models, land use land cover, to estimate the runoff that is generated. So this is how in black and white any green band or red band or any band, every pixel will have either some level of grayness, totally black to totally white, some level of grayness depending on how much is the reflection. High reflection means towards it will be lighter, low reflection means it will be darker. And then you take three such bands, there will be like multiple bands. You take three bands, you combine them, you generate true color. This is true color. Now it is actually a map of Pune, but it is you cannot make much out of it. This is Pune city actually. These dark bodies are water bodies, and you can even see green portions in the Western Ghats. But still, there is lot of disturbance, atmospheric disturbance. You cannot really map everything. For clear mapping, you can make use of false color where the dark body, the water bodies, you can clearly mark the land and water demarcation. And also the vegetation, thick vegetation is here. Some agricultural portions are here. The city is here. So it is much clearer than that, right? So similarly, you can have many combinations for mapping of different features. Finally, one thing before ending this, there are four types of resolution. I talked about spectral resolution. If you are observing on lot many bands, then the spectral resolution is high. It will be useful for distinguishing different features. Then spatial resolution, I think you can all can understand. What is the size of the pixel? Similar to what is the number of megapixels on your camera, how much finer it is. If the resolution is very high, that means your pixel size is small, then you can identify even small feature. So the same location, if it is seen in a Landsat, have you heard of Landsat? Landsat is a satellite, remote sensing satellite series. It is launched by USGS, US Geological Service, NASA. Similarly, there is a Sentinel series, which is European Space Agency. These are freely available open source satellite imagery. Landsat is available at 30-meter resolution. Means this building can be easily identified in Landsat, this whole building. Whereas Sentinel is 10-meter, it is much finer. Then there are sub-meter resolution, like this big bird. Your Google Earth, if you zoom in, you can go up to the smallest field. You can even visualize the smallest field. They actually they take these commercial satellites which are not freely available, and even in our case ISRO has started with their new spatial policy, and they have come up with Bhunidhi portal, where they have kept all satellite imagery of resolution less than 5 meters freely available. You can also create your account and you can download. Otherwise, you can, today we will see how we can download Landsat imagery, Sentinel imagery from different sources. They are openly available. And these are available after every regular periodicity. Landsat imagery is available after every 16 days. Sentinel imagery is available after every 10 days. But because there are twin satellites of Sentinel, effectively after every 5 days you will get one image at 10-meter resolution. So after every 5 days you are getting an image, and you can easily map, like how many of the land use land cover changes you can easily map. You may not be able to map flood because within 5 days the flood may come and go. For that you need to have high temporal resolution, some sensor or some satellite which frequently visits the same point. There is one basic difference between these like communication or geostationary satellites, which are used for INSAT series. You heard of INSAT series, right? Communication navigation purpose. They are at a height of 36,000 kilometers. They continuously see India. They match the rotation of the speed of the earth, and they continuously see, and that is their purpose. Whereas these remote sensing satellites, their height is about 600 to 800 kilometers, and they revolve. They have a polar orbit. So when earth is moving, when they are coming this path, they will be capturing this stream. Again, when they come back, earth must have moved, and they will cover another stream. So there will be some time period before they come back to the same location. That time period is what is known as temporal resolution. Here the temporal resolution is infinity. Always it is seeing the same location. Here in case of Landsat it is 16 days, in case of Sentinel it is 10 days. So if you try to increase the temporal resolution, or if you try to increase the spatial resolution, the other thing will fall down. Means other thing will, you have to compromise. If you increase your height, your resolution, spatial resolution will go down. Like these geostationary satellites, each pixel will be about 1,000 kilometers maybe. They will not be useful for Earth observation. They will be only useful for communication, navigation purposes. Yeah, I know it is. I am getting so much theory. I am just waiting for them to copy. Then we will have a short break, and then we will start our hands-on. Apart from spatial and temporal, there are two other resolutions. Spectral resolution I have talked about. The number of bands, like color photograph, black and white. It is a simple example. In black and white, you have mixing everything. In color, you can identify at least three. There you can identify the colors. But the better example will be that how we can distinguish between clouds and snow. The number of bands where your sensor is capable of sensing, that is the spectral resolution. There is lastly there is something called radiometric resolution, the number of levels of grayness. That will be like if it is a 1 bit, there will be either black or white. If it is 2 bit, four, you can represent different levels of grayness. Now nowadays the sensors they have high like 2 power 10 or 2 power so they have larger capability of representing different variations. Then in this case, it is actually a picture of the same location with different radiometric resolutions. Here the water is appearing in the same shade, even though the depth is different because here the radiometric resolution is less. Whereas here some portion is black, some portion is light. That is because you can get a sense of depth here when your radiometric resolution is high. So that is the radiometric resolution. Four types of resolution in remote sensing. Just like we have color composites, we have different indices for quantitative assessment of, yeah, like it starting with NDVN in literature. We have many other indices, but mostly it is the most popular index, band index, where vegetation has high reflectance in NIR and low reflectance in red, green vegetation. Like this is an example. 0.50 percentage and 8 percentage. 0.50 minus 0.8 divided by 0.5 plus 0.8. The NDVA value is 0.72. Suppose it has some issue of water availability or pest attack and it has turned brown, where the reflectance in NAR has gone down to 40 percentage and reflectance in red has gone up. Red band has gone up by 30 percentage. So then here the NTVI is only 0.14. So this is a measure which can give you some indication about how good or how healthy or how luxurious is your vegetation is. Similarly, we have many indices like NDWI. Wherever NDWI is greater than 0, you can say that is a water body, all these blue areas. You can map your water bodies by taking these two bands, green and NAR bands. And these values always lie between -1 to +1. Why? Because you are normalizing. In literature, there are many other indices. NDBI for building built up area, NDSI for snow areas. Digital elevation model, I have already told that it is a raster model where each pixel has elevation information. And we will see how it can be used for delineation of water, our basins. So I will skip these things. We will be making use of QGIS, which is a free and open source software. ArcGIS is a proprietary software. QGIS you can download on your own laptop or on your system. And we will see we are copying the installation file. I will show you how to make use of QGIS. With QGIS, the advantage is it is free. It has lot of help, like it is an open source software. Many users they use. If you get stuck up with any issue, you can search the error and you can easily get resolution. You can easily get the solution. Whereas it is not easy in case of proprietary software like ArcGIS. One thing is you will not have the flexibility of working on any system. Wherever it is installed, you have to sit there and it is very costly. Whereas, as I said, it has, and also lot of material tutorials are available for learning QGIS. You can go to this website qgis.org where you will find the option for download. You can work on any operating system. Windows, apart from Windows, it can also work on all other operating system including OS, Mac. I will show this at the time of demonstration, and while working with data. So we have the time is already 4 o'clock. We have 1.5 hour. We can have 5 minute break. Huh?
10 minutes will be also after that.
If you have any query, you can ask. Otherwise, you can proceed.
Sir, what is the highest resolution match that we can get for free?
Free,
Yeah.
10 meter.
10 meters, sir.
Sentinel 2. Actually, in Sentinel, you have given radar, active remote sensing. Like Sentinel 1 is radar remote sensing, microwave remote sensing sensor. You will get even, it will be very useful for flight mapping. It is also at almost 10 meter. Sentinel 2 is optical. Landsat is it is an optical sensor, 30 meters.
Sir, let's say that that's not very clear, sir, for doing.
That is, when you are observing, means, because it is 30 by 30 meters.
Yes.
So if you are working at the scale of basin, it will be fine. Basin or surface. If you are working on a very small region, then you have to go for better resolution. Yeah, we can break.
Sir, please step back. जब पूछा कि लव समझे लव क्या
ও এটাকে স্ট্রিম কি করা হবে এটা করে দিস